Alright, so in the next section we're going to be talking about optimization. Oops. Okay, so why would we be doing optimization? Well, the answer is that's how we build functions. And so, just to give you kind of a sense for where we're going with this, suppose I have some data. Let's say x1, y1. Actually, you know what, let's use t's. And the reason we're using t's is these are going to be our targets, our desired values. And so I've got a bunch of inputs and outputs, right? And the goal is to build a function, f of x, so that f of xi is equal to ti. All right, well, what are some ways that I can do that? Well, if you're in CS, you probably are saying, well, why don't you just build a table? Xi, Ti. Right, so then just put in x1, and when you are given x1, just respond with t1. If you get given x2, respond with t2, and so on. Given xp, respond with tp. Well, the problem with this is, well, let's put this in the context of a learning. So we've all been students for a long time. We should know what learning is, or have a sense for what learning is. So when I build a table like this is very similar to in learning, where you just memorize a set of facts, right? So you're just responding to specific inputs with specific outputs. So the problem with this is this isn't really learning, is it? Because what happens if I happen to ask you, well, what happens halfway in between x1 and x2? What would your output be? And the problem with memorizing is that you have no idea. This could be anything. And so we have to have some way of saying, well, if I'm just a small part or a small distance away from x, can I get just a small distance away from the target? And so in terms of a plot, what we're doing, right, is we have these data points, right? And so we're trying to find a nice function that goes through these data points, but we're actually going to not require us to go directly through the data, because if I had to go directly through the data, I might be, well, that's got to go over around here somewhere. I might be actually modeling the noise, because I don't know how much noise there is in this data. You know, if I had data points like this, you know, that was kind of in a band around the function, you know, I might have a function that looks like that then, right? And I wouldn't want to have that. Okay, so there's going to be a little bit of a trade-off. We're going to introduce some error, so we're not going to be exactly on the t's. But because of that, because we're going to allow some error, we're also going to be able to have, we're going to dictate a fairly smooth response to our function. How smooth do we want it? Well, that's a good question. So we're going to try to build a function that is appropriate for the problem. I guess that's where we're heading. So how do we do that? Well, the way we do that is we have a function that has model parameters. So for example, if I have data and I want to just find the line of best fit, then my model would be y equals mx plus b. And so the model parameters would be the m and the b, right? And so do you remember how we did that? Our vertical distances were the errors, and so we said that the error on m and b is the distance between all of these. So we're going to sum all the distances for all the data points. so we're going to be taking the difference between the targets and the model outputs. Model output. And we're going to square that so we don't have positive and negative values in there. Good. All right. So the idea now is that we have this error that depends on an M and a B. And so how would you, or in general, right? So in general, f would be, like y would be some function of x, but then it would also depend on some set of parameters. Okay, so in this case, the parameters were m and b. So this might be a long list of parameters, model parameters that we have to find. Okay. And then our error would be a function of all of these values, right? And then in place of yk, I'll just go ahead and say f of xk, and that's using these model parameters now, right? And so how do I minimize the error? Or how do I find the model parameters? I kind of gave it away. We want to optimize. E, we want to minimize the error. Minimize the error. Okay, and so this is called training. Training. It's the process we take to minimize, or in general, it's to optimize whatever function, optimize error. Some problems will be talking about loss function instead of error function, right? But that's fine. So that's why, in general, right, we're going to be talking about this. Good. Okay. So how do we optimize a function? We had some optimization problems from calculus. What did we learn from calculus? So we had the unbounded. Well, maybe we should start with a bounded problem. Bounded problem. So that was when f just maps the reals to the reals. This was the extreme value theorem. Do you remember what the extreme value theorem said? If f is continuous on a closed interval from a to b, so we're given a closed interval from a to b, then there exists a global max and a global min for f on the interval. And where are the candidates for the extrema? Whoop. Yes, it's where the derivative is either equal to 0, f prime of x does not exist, and these two things together are the critical points, right? And by the way, we're only going to be interested in critical points in our interval. And we have to check the boundary. That is f of a and f of b. And so you might remember what we did in that case, right? We had x and our y, and then here we just check endpoints and critical points. And then we just look for the max and min. Do you remember doing these? Okay, so what was important here is that you had a continuous function over a bounded, actually a closed and bounded region. Okay, closed and bounded region. And then we could use the extreme value theorem. Okay, then we had the unbounded case, right? Where we just said, here is y equals f of x. Find the extrema, global extrema. Now, typically what we would do in this case is we would at least assume that f is probably differentiable. Um, Although you could still look for critical points in that case, right? So, um, but you'd want to put some kind of condition on that. Um, and then what we did is we looked for extrema, or we looked for critical points. And then we tried to see, for example, if this is f prime of x, and this is my number line down here, and this is my critical point, then I looked to see what the sign of my derivative was. For example, if globally on the interval, or on the entire real line, I go from minus to plus, right? And that's the only change that ever is made, then I know that my function is, or has a global maximum or a global minimum right there. Okay, so similarly, of course, if we did the opposite, if we went from plus to minus, right, and we went like that, then we would have a global min, or global max. Yeah, this would be our max, and then this one would be our min. Good. Unfortunately, we typically will not know what's happening outside of a finite domain, and so typically what happens is we're going to get we'll at least have a local extrema. It might be hard in general to prove that it is a global extrema. Okay, so we're going to develop algorithms that will find local extrema. Okay, develop algorithms for local extrema. All right, and so then what you would do is you would run this several times with different initial conditions to see what is your best local extremum. Good. All right, so now we're ready to actually get into our algorithms, and my time is up for now. So I will be back with specific algorithms.